So part 2, Baha. Before we start, I should say that we have, so the 11:30 to 12:30 session are the so-called student talks. So we'll have 3 of them. Alexei Blasenko, who will kind of follow up a little bit what Vincenzo Giuliano will say on quantum kinetic equations. Matt Kaplan, who will talk about high-density nuclear equation of state issues relevant for supernovae, in particular nuclear pasta, and Remy Casaroni, in this really cool thing that I think Tony showed at the beginning of, Tony Mezzacapa showed at the beginning of his lectures, kind of sassy in a box. So that picture you can set up in the laboratory and look at and reproduce the convective pattern. Sassy.
Okay, good morning, everybody. These are too high. How about that? Better. Good. Okay, last time we had seen this network of reactions in the sun, and we had seen that there is a stage equilibration. After you go through all the equilibration stages, basically what you were doing was you were converting 4 protons into 1 alpha particle. And this actually was discovered by Hans Bethe in the early 20th century. But the PP series of reactions was not the first one that he had worked out. The very first one he had worked out was the so-called CN or CNO cycle. Basically, what happens is that if a star is old enough so that it has leftover carbon and nitrogen from the earlier stars, then you can use carbon and nitrogen as catalysts to convert 4 protons into 1 alpha particle. Basically, what happens is that you start with carbon 12, you capture 1 proton on it, go to nitrogen 13, and then a beta decay back to carbon 13, then capture another proton, go to nitrogen 14, capture another proton, go to oxygen 15, beta decay back to nitrogen 15, and then alpha decay to carbon 12. So then you can see that this series of reactions, this was the very first series of reactions that Hans Bethe had worked out. This series of reactions basically start with 4 protons, 1, 2, 3, 4, convert them into an alpha particle, and in the process uses carbon 12 as a catalyst. It starts with carbon 12 and it leaves it as it is. And there are several beta decays which actually also give you neutrinos. This is the simplest cycle that Hans Bethe came up first. Then there is another possibility to include oxygen in the cycle. It actually is very similar. I'm not going to go over the step by step, but basically you again start with carbon 12. After a series of captures and decays, you get back to so this is the CN cycle, and you can have an oxygen extension. Basically, eventually, you also end up with this is another possible oxygen extension. So there are a number of another possible oxygen extension. There are a number of CNO cycles that you can also process 4 protons into an alpha particle in a star. So here is the competition between those 2 possibilities. This is the basically the dominance of the PP chain versus CNO chain. Our sun is a relatively cool star, so it's dominated by the PP cycle, but not completely devoid of the CNO cycle. Now, a question to you guys. Can you explain those 2 curves? With basic physics. This is simply basic physics. There is nothing here that is very deep. Well, there's quantum mechanics. A star is a quantum mechanical object, believe it or not. So what do you think? Why this is the case? Why those two curves cross there? Why at low temperatures PP cycle dominates, but at high temperatures CNO cycle dominates? Yeah?
Well, my intuition is that at low temperatures, PP dominates because of the lower Coulomb barrier.
Absolutely. You're absolutely right. Because of the Coulomb barrier. So if you think about this, what's happening is that two nuclei are fusing. What are the interactions between those two nuclei? There is the, well, these are both positively charged, so there is a repulsive Coulomb force and attractive nuclear force. And everything, the energies, the temperatures are, etc., low enough that the reaction proceeds through the penetration of a quantum mechanical penetration of a Coulomb barrier. Right? You're well below the top of the Coulomb barrier. So if you think about reactions where carbon or nitrogen, the charge on those objects are like 6 or 7. Even if you're capturing a proton, the Coulomb force is 6 times higher than the PP Coulomb force, for example. And as a result, it takes a lot of nuclear force to turn it over, so the Coulomb barrier is quite high. Whereas for the PP series of reactions, the Coulomb barrier is quite low. So at low temperatures, that is to say for smaller stars, then PP series of reactions are the only possibility. Well, they're not the only possibility, but they're the dominant one, because it's much easier to penetrate the Coulomb barrier near the top of it. Whereas as you get heavier and heavier, the CNO cycle also comes into the picture. But since CNO cycle is much more efficient than the PP cycle, the heavier, as you can see, heavier stars, the larger stars, actually then go through the CNO cycle. But nevertheless, Sun has a component coming from the CNO cycle, and that actually is important because CNO cycle uses carbon, nitrogen, and oxygen, which are leftovers from the previous evolutions of the stars, and so it is a measure of what we call metallicity of the star. So before I go on to that, I want to now switch the gears a little bit and talk about how you would model a star. And basically the idea here is eventually to introduce helioseismology to you. So here are the variables that describe a static, stable star at spherically symmetric equilibrium. So I'm going to introduce the pressure, the mass density, the gravitational potential, rate of nuclear energy generation, temperature. These are all, of course, functions of the radius. And then I will have energy flux, entropy, and introduce those two adiabatic indices. Basically, gamma 1 is the derivative of logarithm of the pressure with respect to the density, mass density at constant entropy, and gamma 3 is 1 plus the logarithmic derivative of the temperature with respect to the logarithm of the mass density, again at constant entropy. And also, I will indicate the total derivative, that is to say, derivative coming from not just the explicit time dependence, but also the motion with the capital D dt. So these are the variables I'm going to use. I want to now formulate a static spherically symmetric star. So I need to write basically 4 equations. The first one, this is Newtonian gravity. I mean, simple, nothing quantum mechanical. Basically, I need to write 4 equations. The very first one is equation of motion. That's basically F is equal to ma, but I have written this in terms of the densities. Another equation is the equation that describes the force. Well, the force that the nuclear energy generation compensates is the gravity. So this is the Poisson's equation for the gravitational attraction. Here is G is the gravitational constant, not the Fermi constant, as is in the rest of these lectures. And of course, I have to include, since I'm writing hydrodynamics, hydrostatics, I have to include an equation of continuity. And finally, this is the conservation of energy that takes into account energy generation by the nuclear reactions and the flux produced by the nuclear reactions. So that is what standard solar model is. You solve those four equations simultaneously and get the temperature profile with the pressure profile and so on for the star. Now, this is good, but these days, I mean, solar model or stellar model has been around for a long time, and of course for a long time we could only observe our sun. It was not that easy to observe oscillations of further stars, but now we can actually observe oscillations of faraway stars. So we can actually do what we call astroseismology. So let me then think about what happens. So basically, in order to describe seismology, the vibrations of a star, you have to introduce Eulerian perturbations to the static star. For example, you take here is the solution of those four equations in the previous transparency, rho, r, and t. You basically write that solution as the static equilibrium solution. Let me call that rho 0. And to that, you get a time-dependent perturbation. You add the time dependence part as a perturbation. And then you take this Eulerian perturbation and insert into those four equations and get the equations describing the perturbed quantities. These are the four equations that describe those perturbed quantities. So then you try to solve now these four equations. These four equations together will describe, those four equations together will describe the vibrations of the star. Well, actually, it's quite easy, especially in the case of the sun. You assume that the time dependence is periodic and spherically symmetric. So you take those perturbations, you take out the r-dependent part, you take out, since you assume spherical symmetry, YLM, and then you assume that the perturbations are time dependent. That's actually what's observed. Sun surface vibrates, the solar surface vibrates. Now, if I introduce this quantity, well, this is the adiabatic sound speed. It's basically pressure divided by the density, multiplied by that adiabatic exponent. And c squared here represents the speed of the sound in the star. Now, if I actually introduce this quantity, I call that psi for the reasons that will be clear in a second. If I introduce this quantity, del of the change in the position times the square root of the density times c squared, then you can show that this quantity actually satisfies a differential equation like this. Here, n squared is what we call Buoyancy frequency, given by this expression, and omega CO is the acoustical cutoff frequency, which is given by this expression. Here, h is the density scale height, which is a very common variable that people use in the stars. Sometimes you heard probably polytrops. Polytrops take that density scale height to be constant. Okay, so if you look at this, this is basically an equation that describes the stellar evolution, but that's an approximate equation. And this actually is a problem where you really need computers. You cannot solve this by hand easily. Basically, what you do, you solve these equations numerically. However, it's not that easy to do that because you need to start with the equilibrium solution. So what you do these days, you take a reference model, reference stellar model, and then calculate the deviations from that reference scalar model by solving those equations numerically, and then do a chi-square analysis around that to fit the observed frequencies to what you get. And that, of course, is a very time-consuming task. But here, this equation actually is the reason I wrote it this way is because it's quite familiar to you. It looks like the Schrödinger equation, right? And you are familiar with the Schrödinger equation. Now, here is the sound speed. That's how the sound speed looks like approximately as a fraction of the solar radius. It's a decreasing quantity. Now, in the case of Sun, and that is not true for other stars, and astroseismology deals with all sorts of stars, but in the case of Sun, Sun has two zones. The inner two-thirds is what we call radiative zone, where energy is transported by radiation. Other third is what we call convective zone, where energy is transported by convection. And there's a boundary, of course, between those two. It turns out this frequency n is constant in the radiative zone, but 0 in the convective zone. And the acoustical cutoff frequency is a monotonically decreasing function. So if you look at this equation, this looks like the Schrödinger equation in two limits. In the limit n squared over omega squared is much less than 1. That means that there is like a barrier in the inner part of the Sun. So it's like if you think about this as a quantum mechanical Schrödinger equation, there is a barrier in this limit in the inner part of the Sun, but the other part there is no barrier. So in the other part you have oscillating solution. In the inner part, exponentially decreasing solution in that limit. Those are what we call P modes oscillations of the star. P stands for the pressure. Similarly, if this quantity here omega is the frequency, is much greater than 1, it is as if the Coulomb barrier is shifted towards the convective zone. So the solutions are such that there is an oscillating solution in the center of the star, but they die out as you go to the surface of the star. Those are called gravity or G modes. I mean, obviously, P modes are driven by pressure and G modes are driven by gravity. That's why that's what they're called. Well, you can imagine that they're impossible to observe, very difficult to observe. You have to look for their effect on other variables because they die out on the surface of the star. Whereas the pressure modes actually are maximal near the surface of the star. So by looking at by observing the oscillations of the surface of the star, you can actually determine P mode frequencies. And from the P mode frequencies, you can invert an equation like this. Of course, you have to do it numerically. You can actually get the sound speed inside the star and other quantities. Here is an example of a mode. This is a P mode. Of course, there are many P modes. You have to expand them in angular. This is angular. We expand in YLMs. This is L equal to 3 and M equal to 2 P mode oscillations. Of course, it's exaggerated, but that's basically what you get. And this is how, for example, SOHO satellite had observed those oscillations. This is the angular degree. This is L, and this is the frequency they see. And actually here is probably better how P modes and G modes look like. P modes, this is for different L's. Again, they die out inside the star, but at the surface they are quite maximal. Similarly, G modes are quite dominant in the center of the star, but they die out as you go to the surface. Here, this dotted line is the boundary of the radiative and convective zones. So you can see that you cannot actually observe G modes on the surface. So you need something else. There had been many sort of claims of observation of G modes, but they all disappeared. Whereas P modes are easy to observe because you look at the star optically, and you can actually, you know what you do. You look at the star optically. Originally, we did that for the sun, but now we can do this for other stars. You basically put a millimetric paper on the star, so you have little squares, and you look at red and blue shifts of the light coming from that. Then from that, you can tell whether that little component is coming towards you or going away from you. And from that, you can actually get the frequencies. A typical frequency for the sun is about 5 minutes, and the amplitude of the oscillations is about 100 kilometers. So the solar surface goes up and down about 100 kilometers every 5 minutes, which is nothing for the sun, of course. And the amazing thing is that we can actually observe those oscillations for other stars now as well. Astroseismology is becoming a very important area. So this is one way that you get information about the sun. And by observing these P modes, you can directly compare with your calculations. And then you can determine the sound speed in the sun quite accurately. Actually, if you remember the expression for the sound speed, once you determine the sound speed, you basically determined the ratio of pressure to density. So it's not possible from helioseismology to measure the pressure variations and the density variations or their radial dependence in the star directly. You can actually get the ratio. That's an important constraint on many solar models, and I'll come back to that in a second. Okay, so then these are the observations of the modes. So this is one set of observations about the sun and in principle other stars. So we can do this for the sun and other stars as well. Well, another set of observations is obviously observing neutrinos directly coming from the sun. Unfortunately, that we can only do for the sun. We cannot do yet for other stars. It would be great if you could do this for other stars, but we're not there yet. So there had been a large number of solar neutrino experiments. Let me talk about them a little bit. I'm not going to go into detail, but basically these are huge experiments. This is the Kamioka experiment originally. Basically, it's a water Cherenkov detector. You see the Cherenkov detectors and the water, and you see that there is a rubber boat here. They go around fixing the Cherenkov detectors. And this is the Super Kamiokande. And you can actually see how many Cherenkov detectors they have. And here again is the rubber boat. This is much, much bigger. It's about the size of a football field. It turns out it is the largest water Cherenkov detector you can build. The reason is its linear size is comparable to photoabsorption length in water. Water, the light gets absorbed. If you make it larger, it never makes it to the detector. So for example, if you have a water Cherenkov detector, this is not the historically first one, but if you have a water Cherenkov detector, what happens is that the neutrinos are coming from the sun. They typically have energies up to about 10 MeV, and they hit an electron in the water. Well, electrons have a rest mass about half an MeV. So if a 5, 6, 8, 10 MeV particle hits that electron, then electron starts moving quite fast, starts moving ultra-relativistically. It moves faster than light does in water. So when a charged particle moves faster than light does in a medium, it emits the Cherenkov light in a cone. So then that electron starts emitting the Cherenkov light in a cone. So basically, when the Cherenkov cone hits the surface of the detector, when the Cherenkov cone hits the surface of the detector, then the whole bunch of detectors in a circle light up. So then you know from the amount of the lighting, you know the energy transmitted to the electron. And from the shape of the circle, you know where the neutrino comes from. So you can actually have directionality. And then this is I would say this is a beautiful plot. If you plot it as a function of the cosine of the angle towards the sun, you can see that as you go away from the sun, basically there's only background, but as you get closer to the sun, you get very nice a peak, basically. Neutrinos are indeed coming from the sun. Well, it turns out actually a better way to do that is to use a bit more sophisticated detector. By the way, this character is called Captain Neutrino. It's a symbol of original Sudbury Neutrino Observatory. So basically, this is in Canada. It's the world's deepest nickel mine. It's 2 kilometers down. Actually, it's a beautiful place. I have been down there, actually. You go down in a shaft to this shaft, and then you get off the elevator. It's funny because the 2 kilometers is a long distance for an elevator to go. So they don't actually use electricity for most of the drop. Part of the time you're basically free falling. They just use the electricity to slow down the drop and you reach to the bottom. It's quite interesting. So you put your mining gears and everything, you know, like hooks and the helmet and the lights and etc. And then you know, go there like sardines, you know, you just, because it's expensive, you take down a lot of miners at the same time. So you go down there and then you walk about half a kilometer to the CNO lab site. When you reach the CNO lab site, you get completely undressed and take a shower because it is a clean room. And you wear clean room clothing that they give it to you, and then you go inside, and of course, once you go inside, there is coffee and donuts. I don't know how clean they are, but that is... Well, of course, CNO is not working anymore, but basically what happens, it's a water Cherenkov detector, but it uses heavy water, not light water, so deuterium oxide. So you have then scattering of neutrinos off the electrons, which is good, but remember the electron neutrino scattering from electrons is about 6 times higher cross-section than electron neutrino scattering, and then muon neutrino scattering from electrons, or tau neutrino scattering from electrons, but you get the total light. You cannot distinguish those. With the ordinary Cherenkov detector, you really cannot distinguish between neutrino flavors. But if you have a water Cherenkov detector, you have a deuteron, and the electron neutrino would break the deuteron in a charge current reaction, converting the neutron into proton, basically give you 2 protons, and the electron would go out, it gives you a Cherenkov light, and you have these 2 protons. Whereas if you have any other flavor, including electron neutrino, it can basically break the deuteron via neutral current interaction, so you would get a proton and a neutron, and then you can capture that neutron on some object. Originally, the CNO used salt because that's cheap. When you capture neutron on the chlorine, it excites the chlorine, and then excited chlorine decays into the ground state by photon emission. So by detecting those photons, and you can actually calculate the total cross-section. You can calculate the total flux of the all flavors of neutrinos, and this reaction gives you the electron neutrino part. So if you look at the charge current, let me see. This is the neutral current. This is the charge current. And this is the electron scattering contributions. What's being plotted here is the electron neutrino flux. What's being plotted here is mu and tau neutrino flux. Then you find the place where 3 of them coincide, and you then calculate the neutrino flux coming from the sun, from the data. And then once you know the electron neutrino flux and mu and tau neutrino flux, you know the total neutrino flux coming from the sun. And it's amazing that it agrees with the standard solar model predictions quite well. But as you can see, in the standard solar model, in all the pictures I had shown you, you only had electron neutrinos being produced. But when you do the experiment on Earth, you detect not only electron neutrinos, but also mu and tau neutrinos. And this is, of course, confirmation of the neutrino oscillations. That was the original confirmation. And this is what the CNO had done. It has done in 3 phases. First, it measured the charge current flux. Then it measured neutral current with salt. Then used neutral current detectors, basically helium-3 proportional counters, to detect the neutral current again. So they all agree. Another experiment is Boric-CNO. Boric-CNO could measure the neutrinos coming from electron capture on beryllium-7 in the sun. So those are very low in energy, 0.7 MeV or so. And that's actually important, as we shall see in a second. But here is already, this is a calculation from long time ago, 2003, right after the CNO announced his first neutral current results. What's being plotted here is delta M square for the neutrino mixing versus tangent square of the mixing angle, assuming only 2 flavors. And you see that this is the best fit region. This is fine. But you can also see that you no longer need the standard solar model. These contours here are deviations from the standard solar model. The contour labeled 1, this one, is the standard solar model. Counter labeled 0.95 is 5% decrease from the standard solar model. Counter labeled 105 is 5% increase from the standard solar model, and so on. And you can see that you agree quite well with the standard solar model. Actually, it's almost too well, because there are a lot of errors in the standard solar model. I'll come back to that in a second. So then you can actually, you don't even need to use the solar model anymore in order to get that. If you let the boronate flux free, that is to say, you don't impose the constraint of the solar model, then you get this best fit region quite nicely. Now, more recently, CNO was able actually to lower its energy threshold, and then they saw that in the two-flavor case, there were 3 regions. This region is not really favorable, but there were 3 regions of the neutrino parameter space. This is so-called LMA, large mixing angle, and this is obviously low. It's lower in delta M square. So there were those 2 regions. Typically, the Kamioka experiment, which is a reactor neutrino experiment, preferred this solution. So one could say, well, yeah, that's very nice. This is the solution that we pick. But at this point, there was an issue. The issue is sun produces neutrinos, whereas the reactors produce antineutrinos. So by saying that we pick this region using the reactor neutrino data is an assumption. Assumption is that neutrinos and antineutrinos mix exactly the same way. Now, if CPT is a valid theory, that would be the case. But nevertheless, experimentally, you should be able to test it, right? There's no reason to take it at face value. I mean, you should test it. So then we have not tested that at that time. Well, actually, this is an actually interesting point, because here is the maximum. CNO basically measures neutrinos coming from boronate. This is the maximum of the boronate neutrino flux, 10 MeV. For a 10 MeV neutrino, this is the survival probability of the electron neutrinos coming from the sun, calculated from the theory as a function of delta M square. And this is the CNO's measurement. Again, you see quite nicely that there are 2 places where you you can agree with the data. Now, this was explained by neutrino mixing. I'm sure you had seen this already in these lectures, but neutrino mixing matrix this has just died. This has just died. Neutrino mixing matrix has these 3 components. And that is what we gives us the neutrino oscillations. Maybe I can use this one. Yeah, I'll use this one. This is dying too. Okay, so this is all very good, but of course you had also seen that this is what happens to neutrinos in vacuum. Now, if you have neutrinos going through matter, then things get to be quite different. If the neutrinos goes through matter, there are additional effects. This is what we call MSW effect. You probably had seen this as well already in these lectures, right? But let me give you a physical explanation of the MSW effect. It's very easy to actually think about what it is. So consider the neutrinos are relativistic particles. Consider the dispersion relation, that is to say the relation between energy and momentum for the neutrinos in free space. It's E squared equal to P squared plus M squared, right? That's the relationship. Now, in matter, if you put those neutrinos in matter, they interact with the matter. Imagine that the matter acts like a potential. Well, if you write down a Dirac equation, that's a 4-vector potential. It will have a scalar component and a 3-vector component. The scalar component will modify the energy, and the 3-vector component will modify the momentum. So if I call the, thank you, if I call the energy component of the potential, scalar component to be V, and 3-vector component to be A, that's the potential given by the matter, by the background, then I can rewrite this quantity by expanding in powers of V and A as E squared plus P squared, but you no longer have just m squared here, but additional contributions coming from those terms. So that's all very good. But let's think about what these things can be physically. I mean, you can, of course, calculate them. That's fine. But scalar component has to be proportional to a scalar quantity describing the background. What are the scalar quantities that you can think of describing the background? Only electron density. If there are neutrons, maybe neutron density and proton density separately. But if you don't have neutrons, and sun doesn't really have neutrons, free neutrons, you don't have to worry about neutron density. So it's only electron density. V, the scalar component of the potential, has to be proportional to electron density because the only scalar quantity that describes the background. Well, what about the vector quantities that describe the background? Let's think about vectors. What vectors can the background have as a background, as a macroscopic background? Well, it can have polarization. If there are strong magnetic fields, the charged particle can be polarized. There could be a total polarization. Or it can have matter currents. You may have matter flowing around. So it can have currents, matter currents, charge currents. I mean the currents of electric charge. I don't mean charge current of the weak interactions. So either currents or polarization. So if there is a polarization, it will be proportional to the total spin of the background. If there are currents, it will be proportional to that current. But if you say your star is static and charge neutral and unpolarized, that is to say small magnetic fields, all those quantities have to average out to zero. They could be microscopic currents, but overall they will average out to zero. So you don't have to worry about that. So A has to be zero, and the scalar component of the potential has to be proportional to density. And of course, you can calculate what that is from these diagrams. And then you find that, of course, there's a Fermi coupling constant in the front, and Fermi coupling constant in the front, and a factor of square root of 2. Well, Fermi coupling constant is obvious because it's a weak interaction. So you can get this part from physics, square root of 2, you have to do the calculation. Similarly, neutron background provides this through the weak neutral current. Now, you can actually write down a similar term with Z exchange, but Z exchange contributes the same to all neutrino flavors. Right? In the lowest order. There are loop corrections to what we call loop corrections in particle physics. And remember, in the loop corrections, you can put charge leptons. And if you think about charge lepton masses, electrons are much, much, much lighter than tau. And even muons are much lighter than tau. So if you go to the loop corrections, that is to say, if you go to a dense enough medium where the loop corrections are important, you can actually distinguish muon neutrinos from tau neutrinos via second order neutral current contributions. This could be an important thing in very dense astrophysical media. Of course, there's another thing. This term, Z exchange term, does not contribute to a sterile neutrino. So that's another place where you have to be careful. But if you ignore all those, if you say, well, I'm in the sun, not in a star, the density is low enough, so I don't have to worry about the loop corrections, which is fine in the sun, and you ignore the sterile neutrino, then you can ignore the Z exchange term. Also, I should point out that the matter effects induce an effective CP violation, which is not surprising because universe is CP broken. It's not CP symmetric, right? This room is not CP symmetric. I only see students. There are no anti-students here, right? So we are not CP symmetric. So matter effects violate CP. So when you look for CP violations with neutrinos, either in vacuum or in matter, especially if you use some astrophysical side, you have to take out the CP violation due to the background. Okay, so then in the two-flavor limit, for example, then you solve an equation like this. I'm not going to go into detail, but then the evolution will depend not only on the mixing angles, but also the matter background. Now, this is all very good, but how does that help us to distinguish between two solutions of CNO? Right? That was our original goal. Well, it does in the following way. Here is the difference between summer and winter in the northern hemisphere. So here is the Earth, and this is where the Neutrino Observatory is. And the Earth during the summer is tilted towards the sun. Summer in the northern hemisphere is tilted towards the sun. By the way, they asked this question, what's the difference between summer and winter in the Harvard graduation to the graduating seniors? And only about 20% knew the correct answer. But in the summer, so this is the situation.
That means that 80% got their money's worth.
80% got their money's worth, exactly. So in the summer, during the day, the Neutrino Observatory will be observing neutrinos coming from the sun directly. Of course, it's underground, 2 miles underground, but 2 miles of Earth is nothing. At night, the Earth rotates, the observatory rotates, it comes to there. Well, sun is, of course, still in the same location, more or less. And then the neutrinos, to reach to the observatory, have to go through the Earth at night. So if the matter effects are important, there will be a difference between neutrino flux observed during the day and at night. And you can measure that. Similarly, there will be a seasonal difference, because during the winter, the Earth is tilted away the other direction. And as you can see, that neutrinos go through even longer, more Earth. So if there is a matter effect, then you also, in principle, expect possible difference between summer and winter. So you can actually calculate that day-night asymmetry. This is the definition of the day-night asymmetry. You can calculate that. And this is the asymmetry for this 10 MeV neutrino as a function of delta M squared. This is the calculated asymmetry using the standard solar model. And this shaded area is what CNO observes. Unfortunately, you can see it still agrees with both solutions. This is bad. So you need to shift this peak around, right, in order to see. You need to shift this peak to lower energies. Indeed, it does shift to lower energies for lower energy neutrinos. Well, a lower energy neutrino is the neutrino coming from the electron capture on beryllium-7 in the sun. And that can be observed using Boric CNO. I mean, that's chi-squared. I'll skip that. So that's how it looks like for a neutrino with 862 keV, 0.8 MeV energy asymmetry. And those neutrinos can be measured in Boric CNO. And this is the Boric CNO's measurement for the asymmetry. And you can see it rules out this low region. It agrees very well with the LMA. This is a very new result, by the way. I mean, one thinks that solar neutrinos are an old field, had been around for a long time and so on, but this result is only 1 year old. So only recently, using solar neutrinos, we were able to show that the LMA region is the favorite region for the solar neutrinos, and that happens to be exactly the same region for the reactor antineutrinos. That is to say, within the experimental accuracy, neutrinos and antineutrinos mix exactly the same way. So this actually tells you astrophysics really can help you to do a lot of such observations. And here is very recent result. This is from Super Kamioka. This is this year, the asymmetry observed in the Super Kamioka compared to solar and Camland asymmetries. Okay, so that's all very good, but I promise to you that I will tell you something about CNO neutrinos. So let me go back to them, and let's think about the assumptions in modeling the sun. And let's go back to astrophysics if you wish. Here is astrophysicists or astronomers' periodic table. For astronomers, there are only three elements, X, Y, and Z. X is hydrogen, Y is helium, and everything else is Z. Well, these are the fractions, of course. X, Y, and Z are fractions, so they add up to 1. Everything else is Z, and they're called metals. For an astronomer, oxygen is a metal, which I never understood, but apparently it's a metal. So anyway, in the standard solar model, one assumes that the protosun, at the beginning, the sun follows, I'm not going to go into the details, but what we call a convective HiPACC track. That is to say, 0H sun is homogeneous. That's the assumption. That means the metals in the original protosun are the same as the metals we observe on the surface of the sun today. So then, initial parameters are initial helium abundance, initial metal abundance, and that also gives you initial hydrogen abundance, so they have to add up to 1, plus the mixing length. Then you evolve the sun to today forward to produce the current observed radius of the sun, luminosity of the sun, and surface abundance of the Y, of the helium. Now, it turns out the surface abundance today, deduced from the photospheric absorption lines, were recently reevaluated using three-dimensional methods. Before, we couldn't do that. Again, this is due to advances in numerical methods. And it turns out what we had seen today as the metallicity of the surface of the sun does not agree with the original metallicity that we assumed in the standard solar model. This is actually not so bad. This actually fixes some old puzzles. If you think about, if you look at the basically helium abundance of the sun as a function of the oxygen abundance, everything nicely for all the stars set on a straight line, but the sun was right there. It was an odd star. It was an odd star somehow enriched in heavy elements. But the new abundances, this actually pushes back to the straight line where all the other stars are. So clearly we have faith in this new abundance. It brings the sun in agreement with other stars. But it creates new ones. This is the solar sound speed. I don't know if you can read that, but this is the deviations from the standard solar model. This is the solar model, and these are the deviations. The dark black curve is the original observation, and if you take the new observation and invert that, you get this quite discrepancy in the. So clearly, you deviate quite a bit in the sun, within the radiator zone of the sun. So in some sense, there's a mismatch between the surface of the sun and inside of the sun right now. Well, what does that mean? That actually changes the metallicity of the sun. And remember, CNO neutrinos are still not measured. So since the metallicity has changed, that is to say, C and N and O abundances changed, that actually changes the flux that you expect, neutrino flux you expect from the CNO cycle. And what's being plotted here is the beryllium-7 neutrino flux in units of 10 to the 9 per centimeter square per second for the, this is the old model of the sun. These are the values calculated using the new abundances as compared to data. And these shaded areas are the errors. Now notice that theory has more errors than the observation. I'll come back to that. It's actually an interesting question. One can reduce these errors. But you can see that the observation cannot really distinguish between old and new abundances. Whereas, again, if you look at the boron 8 neutrino flux, this is old, this is new, and this is the observation. Again, you cannot distinguish between the two because changing metallicity doesn't really change much those PP abundances. But the changing metallicity changes the CNO abundances quite a bit. So this is the neutrinos coming from oxygen 15. Old abundances, new abundances. It's reduced quite a bit. Of course, there's no data. So in principle, if you can measure the CNO neutrinos coming from the sun, you can distinguish between these two. The effect is even worse for fluorine 17 neutrinos, old versus new. So you can see that there is actually astrophysics still to be done with the neutrinos, with the solar neutrinos, if one can measure those neutrinos. And it actually tells you something about the metallicity of the sun, which is a bigger question about the evolution of, main sequence evolution of the stars. Now, let me go back to and go over this error budget. I mentioned that the theory has more errors than the observation. And this is where the errors are coming from. About percentage-wise, the total altogether, you have 14% or so error in the sun. The 2.7% comes from the diffusion coefficient. That is still somewhat unknown. And other input parameters are about 0.6%. But the biggest two errors are coming from the knowledge of neutrinos, weak interaction, what we do not know about the weak interaction, mainly theta 1,2, the neutrino mixing angle theta 1,2. So you can actually measure theta 1,2 better, and there are experiments that are being prepared to measure theta 1,2 better. Then you can actually reduce that error on the standard solar model prediction. But most importantly, the biggest error, 10%, almost 2/3 of the error, are coming from the nuclear reaction rates. These two reaction rates, proton on beryllium-7 and nitrogen-14 on proton and nitrogen-14, are not actually as well measured as they should be. So these are actually not that easy experiments, obviously, because you need to measure those reaction rates at the stellar temperatures. They are very low. Yeah.
What is your axis on the beryllium P to gamma?
Oh,
Is that MEV?
that's MEV. So let me go over separately. So for the reaction helium-3 on alpha, which gives you beryllium-7, and then eventually beryllium-7 captures an electron, gives you boron-8, right? And then proton, or captures a proton, gives you boron-8. So that's the initial reaction. It turns out this reaction is the main uncertainty in the sun and also for the Big Bang nucleosynthesis. So it's the same reaction, of course, different energies. And it still is not as well observed, as well measured as it should be. The other reaction, which actually is the main error in the CNO cycle, and is the neutrinos coming from, well, the nitrogen-14 proton capture on nitrogen-14. And as you can see, there is quite a discrepancy between different observations, different measurements, and this is where you need to know it, and obviously there is no data. So there is still a lot of astrophysics that one can do, solar physics that one can do using neutrinos. It's not an finished subject that you may hear from some people saying, well, we know everything there is to know about solar neutrinos. Well, we have measured some of the PP chain very well. But, you know, there are actually 3 kinds of solar neutrinos. I've been only talking about one kind. That is the neutrinos coming from the nuclear fusion reactions in the sun. And the most dominant one there is the one coming from the original PP capture. But the measurement that has measured them, there were 2 experiments that had measured them, SAGE and GALEX. They had a rather high threshold. They only measured a fraction of them. Whereas the PP neutrinos coming from the proton capture on proton go down to quite a few energies, go down in energy quite a bit. You can go down all the way to keV energies. And most of that flux has never been measured. That's an actually interesting experiment, very hard, but it's probably possible. It's really hard to get funding for it, unfortunately. It's not cheap. So this is one kind of solar neutrino. Now, there are other kinds of solar neutrinos that I haven't talked about yet. And I'm not really going to talk about in detail, but let me mention what they are. There is a second kind of solar neutrino. Can you guess what it is? No, but there is nothing radioactive in the sun. But remember, the center of the sun, we were talking about this with George. In Russia, under the Landau school, everyone had to take plasma physics as a class. Center of the sun is actually plasma, a very hot plasma. And very hot plasma can convert energy in the plasma into particle-antiparticle pairs. And you can actually produce neutrino-antineutrino pairs from a plasma. Well, of course, the temperature of the plasma has to be larger than twice the mass of the neutrinos, but we think that the neutrino mass is sub-eV, whereas the temperature in the sun, in the center of the sun, is MeV. Well, 10, 15 MeV or so. So in principle, you can produce neutrino-antineutrino pairs. As a matter of fact, you don't even need, well, you need to have the temperature greater than twice the mass to produce them in copious amounts. But remember, neutrinos obey a distribution, Fermi-Dirac distribution. There's a tail of everywhere, so you can produce anyway from any plasma. As a matter of fact, the plasma right there in that light bulb is producing neutrinos because the energy there is keV, EV. So it is producing maybe 1 or 2 neutrinos a day, but not much, but maybe even a fraction of them, but it's producing neutrinos. Whereas the sun is producing copious amount of neutrinos from plasma. And they reflect the central core temperature of the sun. The energies of those neutrinos reflect the central core temperature of the sun. They have never been measured. Now, this is a great project for an experimentalist. I don't think we have any experimentalists here, but a great project for an experimentalist, because if you measure them, you're guaranteed to get a big prize. I mean, think about the cosmic background neutrinos have not been measured, and they are even lower energies. It's very hard to measure them, but I suspect plasma neutrinos will be measured within your lifetime. So that's a second kind of neutrinos. And the third kind is a speculative kind. These are very energetic neutrinos coming from the center of the sun, because the sun is a gravitational well. It basically accumulates WIMPs, if the WIMPs exist. Well, this is now becoming fancy land, but you know, if WIMPs exist, it will accumulate WIMPs, and then they would annihilate one another and produce neutrino-antineutrino pairs. They would produce other things, but neutrino-antineutrino pairs would escape, very energetic ones. So in principle, if such particles exist, since sun is a gravitational well, it will produce very energetic neutrinos. This is the third kind of solar neutrinos. We have not obviously seen them either. And this is speculation, but the plasma neutrinos are not. They're real. They're there. They have never been measured. Not only plasma neutrinos, which are keV energy, has never been measured, even the low end of the PP flux has never been measured. Only the very high end of it has been measured. So these are actually interesting questions, and measuring those will tell us quite a bit about the sun. Okay, now I'm going to switch gears, and I'm going to start the supernova a little bit, George, and then I'll stop, okay? All right, so.
I'm sorry,
yeah.
Just one comment before you go back to the mundane issue of nuclear physics. Under the solar gamma peak down there at a few tens of keV,
Right.
there's other things besides just the direct nuclear reactions going on. For instance, you have, as you mentioned, the plasma, so there's screening effects.
Right, I didn't mention that.
Interesting problem from the perspective of nuclear physics as well. The treatments of screening are fairly rudimentary, that I would say. Saltpeter approach is basically what happens, but you can do better.
Well, there is a problem with the screening. You're absolutely, I didn't mention that because that takes us even further away from astrophysics, but indeed you're right, because these reactions are not taking place in the star in a free medium. There's an electron cloud around, as I say, it's a plasma. So there is a screening of the electric force. And typically, what we do is treat screening in the adiabatic approximation. But that doesn't seem to, I mean, you expect that to be the maximal effect, but doesn't quite even explain the data. There are all sorts of issues with the screening that I don't know if I can get into, but you're absolutely right. You're right. Okay, so let me start saying a few words about supernova neutrinos, and I will continue with that. This is a beautiful picture from Los Alamos Science. I love this picture. The neutrinos are coming to Earth not from the sun, but also from distant supernova. It's a watercolor picture, I think. And this had been measured. This is not a speculation, has been measured. In supernova 1987A, Kamioka was operating, IMB was operating, Baksan was operating, has been measured. This is the measurement of Kamioka as a function of time. Kamioka is a Japanese experiment, so this is Japanese, but it says background in Japanese, this line. And you can see that until the explosion, the background is more or less constant. Then supernova explodes. You get this nice peak of the neutrinos. These are the neutrino events. So basically, you start with a progenitor star, which has at least 8 times the mass of the sun. And we prefer them to have 12 times the mass of the sun, but 8 to 12 times is fun too, but slightly different. And in this process, in the collapse, you release something like 10 to the 53 ergs of energy, which is about 10 to the 59 MeV. And 99% of that energy is carried away by neutrinos and antineutrinos. So altogether, if you say average neutrino has a 10 MeV or maybe a little bit higher energy, then you have something like 10 to the 57 or 10 to the 58 neutrinos. So for the purposes of my talk, actually tomorrow, I guess, supernova are factories that convert gravitational binding energy into large amounts of neutrinos. So that's, and of course, there has been significant developments in modeling these supernova. Recently, there had been 2-dimensional and 3-dimensional models, and they display a complex interplay between turbulence, neutrino physics, and thermonuclear reaction rate. And I'm not really going to go into that, but I just wanted to mention. What I'm going to do today, tomorrow, is I'll tell you about neutrino effects in such an environment. So I'm going to stop here, and then we'll continue tomorrow.
Questions? Can you use, or can anybody use like neutrino observations from the sun to try and constrain those nuclear reaction rates to some degree?
No, that's a very interesting question, and it's not something funding agencies would like to hear. In principle, yes, but of course, originally those experiments were designed to measure neutrino properties or the solar properties, not the reaction rates. But indeed, for example, the Sudbury Neutrino Observatory measures the neutrino-deuteron interactions, right, to get the neutrino rate. Well, if you think about, for example, can you turn it around and determine the neutrino-deuteron cross-section from those observations? Yes, the answer is yes. The way you would do that is the effective field theory. You use effective field theory, as we talked about. Basically, neutrino capture on deuteron, and you can integrate over everything else in the effective field theory because you're well below the pion mass. Neutrinos are not that energetic, well below the pion mass. So then you write a Lagrangian, an effective Lagrangian, to describe that process. And there's only one free parameter. If you remember, effective Lagrangians have free parameters that you have to fit with data. There's only one free parameter for that effective Lagrangian called L1A that represents the axial vector coupling of the neutrino. And so you can actually calculate the cross-section as a function of L1A. And you expect L1A to be about couple Fermi, inverse Fermis. So you can actually then turn around and use the solar neutrino data to determine what L1A is. Yes. But this is not something funding agencies like to hear because they're not spending millions of dollars to measure nuclear reaction rates. So you have to be careful. But indeed, yes, you can do that. And it has been done in one case.